and go from current slide and turn on the projector. Again, now I've announced this one before. I'm just going to make a guess, or either you're going to be here next fall. You won't. I didn't think so. If you know of anyone who will be here in the fall and will be needing to complete a FAFSA, that's a free application for federal student assistance, they need to do it now, because we're going to a new operating system, brand new, totally different operating system. Nothing in our old system will pull up into the new system, I don't think. They're completely different architectures and everything. So they're trying to get everyone who is going to be here applying for student aid in the fall to get the FAFSA done now, because they have to enter everything else from scratch, everything from scratch. And that includes oops. All right, he came in late. Okay. So please, if you know of anyone who will be here in the fall, please encourage them to get their FAFSA done now so they can get it in the system, and you won't have a delay, and it'll help them out a lot. Okay, this morning they had the college transfer fair days on the Birmingham campus. Tomorrow they will have it on this campus, and this will be from 9:30 to 11:30 on this campus in this building. I'm guessing somewhere around the cafeteria. I kind of doubt if it'll be in the cafeteria. They may have a few tables in there. I guess in the faculty staff dining room, they probably have quite a few tables in there, possibly in the hallways on either side of the cafeteria, even in the front entry area, the admissions area. So that's coming up 9:30 to 11 tomorrow here on this campus. And you're running out of time to get the application for the summer research opportunity at University of Illinois, Arkansas, and Howard University for that 10-week internship. Fantastic program. There are others out there. Some of the deadlines may have already happened. Others may be in the future. But check them out and do what you can to participate in those. It's quite a good opportunity. Okay. Now, I can't think of anything else to hit on here. I'm making a guess here, since you weren't here to hear it last time. Are you going to be here in the fall? I didn't think so. Okay. If you know of anyone who is going to be here in the fall, FAFSAs for fall need to be done now, okay? Because we're going to a brand new operating system. The student suite, no longer. Nothing else will be the same. So everything that we did, and the new system and the old system will not communicate at all. They're completely different architectures, everything different about them. And so if you know of anyone who will be here in the fall, who may be on FAFSA, done a FAFSA for this year, they need one for next year, they'll say, hey, I can wait until August and get that done. No, they can't, because everything has to be entered as if you're a brand new student in this new system. And so they need to get the FAFSA done now, so you won't be clogged up with all the other new students coming in the fall, because the system will think you're a brand new student, because that has no alternative. So let people know that. Get it done immediately, if not sooner. Okay. Any questions on anything we've done up till now? All right. We were doing example 5 last time when we ran out of time. Okay. I don't want to go back and do. Well, wait a minute. No, we didn't. We finished example 5. It was the thing at the bottom of the page that where we were beginning today. So it wasn't example 5. We did finish example 5, I think. Did y'all get that we did?
Yes.
Okay. Yeah. Yeah, here's where we begin today. From the theorem 1113, which is near the top of page 792. By the way, we're in chapter 11, vectors and the geometry of space. 11.5 is lines and planes in space, and we're on page 792. And this is near the bottom of that page. The theorem is near the top of the page. From this theorem, 11.3, you can determine that the distance between the point P, x0, y0, z0, and the plane ax plus by plus cz plus d is equal to 0. Now, what you're assuming here is the point is not on the plane. Okay? So the distance between those would be, let's see. Let me go back in. Oh, wait. There it is. There is the distance formula that was given there. Okay? All right. So, the normal vector to the plane, remember, is are your direction numbers here, A, B, C. That's your normal vectors of that plane, okay? So, with that in mind, and the fact that the PQ, PQ is the okay. They don't show you P here, but P is a point in the plane, and so is, I'm sorry, Q is a point outside the plane, P is a point in the plane, and the P is x1, y1, z1, okay? So, the dot product between PQ and N, okay, would then be the components of PQ multiplied by the corresponding component of N divided by the magnitude of N. Okay? Whoa, going the wrong direction. Okay? So, this is your N, A, B, C. Okay? The point PQ would be x0 minus x1, y0 minus y1, z0 minus z1, because the P is point x1, y1, z1. Okay? So the dot product between that would be, and it's the magnitude of the dot product, the absolute value of the dot product would be A times the first plus B times the next plus C times the next. So that's your numerator. And then your magnitude of N is just the square root of A squared plus B squared plus C squared. Or, now, here's where the magic comes in. A times, minus AX1 minus BY1 minus CZ1 is the value of that D that was in your, I don't know if it's going to show it anywhere. Yeah, in this equation here, okay? Because, remember, this is a point in the plane, and this is the normal, and the point in the plane to the normal I'd have to go way back in the slide, but if you go back in the slide or in your book, you'll find the equation that relates that. Let me see if I can find it in the book rather than having to probably not going to be able to find okay. Yeah. If you go back to Theorem 1112 on page 788, okay? Let me do it quickly. Okay. Whoops, was that it? Nope, that's 1113. Getting closer. There it is. Okay? Remember, standard equation for a plane in space, that's a normal vector. We just were talking about that. The point in the plane, x1, y1, z1, would be ax minus x1, that was this is the equation for the plane in space, where x is any point on the plane, x1 is a specific point on the plane, then this would be ax, so you have a minus ax1 here, minus by1 here, and minus cy1 is cz1 here, and those added together give you d, because ax plus by plus cz is here, and those parts would be the d. And that's why it said the d, that's where they get the d. We'll get there one of these days. Close, 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 close. There we go. D was this value here. Okay? That's what we remember from before. So, if you take a look at this then, if you know the A, B, and C, your direction vectors, that's from your normal vectors, and if they happen to give you that plane, you got that, and basically all you do is take the point Q that you're measuring from, that's outside the plane, plug that in here, in that form right there, and divide by the magnitude. That's the distance of a point, between a point and a plane. Okay? You don't need to know this point here at all, except if you don't know what that D is, then you need it to figure that out. But if they gave you the point and the plane, you got it. You just plug. That's all you have to do, besides marking right here. Okay. Okay. Now, goodness, I thought we'd already done that. I need to get back to the page I was originally on. Okay. They're skipping example 6. I was looking for that. So let's go back and see if we can do example 6 here. Okay. Whoops. Didn't get my pen set up. All right. Finding a distance between two parallel planes. Two parallel planes, 3x minus y plus 2z minus 6 equals 0. That's a plane. And 6x minus 2y plus 4z, oops, plus 4, sorry about that, plus 4 equals 0. Now, how can you tell these two planes are parallel? Well, the normal vector for this one is 3, negative 1, 2. Normal vector for this one is 6, negative 2, 4. They're just multiples of each other. So the normal vectors are in the same direction. They've got to be parallel planes. Unless they happen to be the same plane. Could they be the same plane? No, the dead giveaway here is this is a minus 6 here, that's a plus 4. Every value, and these first three were doubled here, and this one is way off from being doubled from that. So these means these are parallel planes. Okay. All right. Two parallel planes are shown in this figure. Okay. To find the distance between the planes, choose a point in the first plane. Oh man, how are we going to choose a point in that plane? Any value that makes that equal 0. Any value that makes that equal 0. So why don't we just choose our, I would even say, I'm going to do a different one for one they did. I'm going to say let x and z be 0, and then y is equal to minus 6. Right? That works, doesn't it? 0, minus 6, no, minus a minus 6. It's plus 6, plus 0, plus minus 6 is 0. Okay? Sure. So here's a point in that first plane. Or the second plane, it doesn't matter. Just pick a point. And we said 0, minus 6, 0. That point is in that plane. Okay? 0, 6, 0, minus 6, that's equal to 0. Got to be there. Okay? Now, that's all we need. And now we plug that value into this expression. Okay? And divide by the magnitude of the normal vector. So that would be 0, 12, 0, plus 4. So that's going to be 16, right? Divided by the magnitude of your normal vector. Now, which normal vector do we use? It doesn't matter. They're the same. Well, it does sort of matter. We use the one that we're going from. So that would be over the square root of what? Normal vector to this plane right here. Anybody? 6 squared, which is 36, plus 4, plus 16. I'm pretty sure that is 16 over 50, square root of 56. Is that right? Okay. Now, are there any perfect squares lurking inside 56? I'm trying to remember. Half of 56 is 28. So 4 will go into 56. I don't know why it does this. Okay, 4 will go into 56 14 times. So this would be, I can't get it to right. Okay. This is really, that was squirrely early this morning and never has changed. So this will be 16 over, factoring out of 4, square root of 4 is 2, times square root of 14. This will be 8 over root 14. That should be the distance, between those two planes. Didn't matter which point you chose. Yes? How did I get the what?
The 16.
The 16 up here? Yeah. Okay. I picked this point here and plugged it in. I got that from here, okay? Got this point from here. Plug it in to x, y, and z here. That would be a 0. That would be a minus 2 times minus 6 plus 12. That would be a 0 and plus 4. So 12 plus 4 is 16. That gave us the numerator. Okay? Okay. Let me go back. No, go ahead. Oh, there it is. This is that distance formula that I was just using. This is the absolute value of the, pick a point in a plane, okay? Pick a point outside of the plane that you're interested in, plug that value into the equation of the plane, okay? Now we picked a point, 0, -6, 0, okay? And then plugged it into the equation for the plane that it was not in, okay? The other plane, that point not in the plane, and that was the one, the second one there. And then divide by that A, B, and C of the magnitude of that vector, okay? So let me go back, I think, yep, there it is, here. So we got the point from this plane, plugged it into this one, because this point is not on this plane, okay? Plugged it in here, that gave us our numerator for the distance formula, and then the denominator is the magnitude of the normal vector to that plane, which was this one. And that gave us our 8 over root 14, which they actually calculated to be something around 2.14. That's the distance. Does that make sense? Yeah.
So, is there a reason why we didn't use theorem 11.13?
Why didn't you use what?
Is there like that formula that's on the board for example 5?
Yeah.
That formula there?
Right.
This is the point plane formula?
Right.
Is there a reason why we didn't use that? We didn't use that?
It was shorter and I was lazy.
Okay, so
it was easier to do. Huh?
Could you use either?
Yeah, I mean, that's the same thing. If you did the dot product, okay, you still have to get a point, okay, and we got this one. You didn't have to use this one. They actually they let y and z be 0, and then the x had to be 2, so 2, 0, 0. That's the one they put in, okay? 2, 0, 0 works here. Plug that in there, okay? It doesn't matter what point you use, okay? But then you would, the reason you didn't use, let's see, yeah, you would have to find another point on this point, okay? And that's easily done too. Probably the easiest one would be for both of these to be 0 and have a 0, 0, -1. So there would be another point. So then you could do the vector between those 2 points, any 2 points from this plane to that plane. You know, they're parallel, none of them are in common. And then you could do dot that with the normal vector here, which you know is 6, -2, 4, and then divide by the magnitude just like we did here. So yeah, you could do that. You want to do it just to see? Oh, okay.
We can.
So again?
We can.
Yes? Okay. So those 2 points that I happened to choose because I figured they did it a little easier. 2, 0, 0. That's the point in this plane. And this one was 0, 0, -1. Okay. So the vector between those two would be 2, 0, 1. Agreed or not? Vector between this point and that point. Okay? So there's our PQ. We're going to dot that with 6, -2, 4. That's the normal vector for this plane, right? Those are your direction numbers. You just pull it off of it, okay? And then we're going to divide this by, we've already done the figuring here, 2 root 14. We've already done that. That doesn't change here. So what's the dot product here? 12 plus 4 over 2 root 14. That'd be 16 over 2 root 14. And that's equal to 8 over root 14. Okay?
How did you get the vector 2, 0, 1? Our PQ?
This one here? Or
Yeah,
this
so
one?
that, in between those two coordinates, you got vector 2, 0, 1.
2, 0. Oh, I'm sorry, that's 200. Sorry about that. No. No. This is the vector PQ. This is P. This is Q. That's P. Doesn't matter which way you do it. I just did it this way. And then do 2 minus this would be 2. 0 minus this is 0, and 0 minus 1 is plus 1.
0 minus 2 is what?
Okay. This is the point Q from that plane, from that plane. No, from this plane, sorry. Duh. Okay. Q is from that plane. P is from this plane. Okay. Now, how do you get the vector PQ?
Initial minus 2.
Yeah, final minus initial. And this is the initial, that's the final. So 2 minus 0 is 2. 0 minus 0 is 0. And 0 minus a minus 1 is a plus 1. Okay? I could have used this point up here. That would have worked too, But I chose this one because the numbers are smaller and I was lazy. Okay? And it was positives. Okay? All these reasons, it doesn't really matter. Okay? And the normal vector for this plane came out of here, as did the magnitude of that normal vector. So do it and you get it. Yes?
Could you have used the normal vector from the other plane? So
Yeah.
3, -1, and 2. Could you
Okay. Same 2 points, but do the normal vector there. Let's try it. Same 2 points will produce the same PQ, right? So that would be a 2, 0, 1, right? Agreed? Okay, dot that with the normal vector from this plane, which is 3 minus 1, 2. Okay, but then you have to divide by that one. The square root of 9 plus 1 is 10 plus 4 is 14. Okay? Now, without doing any work on it, I want you to notice this. If I multiply this by 2 here, don't I get this one? If I multiply 2 by this, I get that. Right? 2 times this. You multiply 2 by this, and you get that. So, this is exactly the same thing. Okay. So, that okay?
Yeah, I was just figuring out the
All right. Why we did the other way, they basically gave us a shortcut, and we used it. There was a shortcut. Yeah, just plug in the A point from the other vector, other plane, into the formula using the direction numbers from the second plane, whichever level. Okay. Now, yeah. I think this is where we... The formula for the distance between a point and a line resembles that for the distance between a point and a plane, except that you replace the dot product with the length of the cross product, okay? And the normal vector in with the direction vector for the line. Oh, that's just like it, isn't it? Except for this and this, it looks just like this, except it doesn't. I'm sorry. Okay. So here is theorem 1114, distance between a point and a line in space. You would think a line would be simpler than a plane, but it's a little more complicated. The distance between a point P and the line in space is the magnitude See, before it's just absolute value. Now it's magnitude, because this is a vector, the other is a dot product, which is a scalar, so then you just need absolute value. Here you do the magnitude of the PQ cross U divided by the magnitude of U. Okay? Where U is the direction vector for the line, and P is a point on the line. Q is a point off the line. Okay? So P is any point on the line. Q is any point off the line that you're trying to get the distance from, and U is the direction vector for that line. Okay? Oh man, they don't even do one. So let's do example 7. So let's back up, and back up, back up, back up, and let's do example 7 here.
I have a question.
Yes?
Is there a reason why they're using U as the direction vector instead of N?
U.
Is there a particular reason why they're using U instead of N?
Instead of N. Okay, because N means normal vector. U means a direction vector. I mean, U is any vector, but we're using it as a direction vector. Okay? So this will be our review of what we mean by that. Example 7. Find the distance between the point Q, now this is point off the line, of 3, -1, 4. Somehow that seems familiar, but maybe we use it somewhere else. No, we use something similar to it. Okay? And the line is given by these parametric equations. X is equal to -2 plus 3t. Y is equal to -2t. And Z is equal to 1 plus 4t. Okay. Now, I hope I copied it right. Now, we want the distance between this point that's not on that line. How do we know it's not on the line? Well, let's see. What would it take to make, let's start easier, to make -2t equal to -1. That would mean t would have to be 1/2, right? Okay, so therefore if you put a 1/2 in here, you get 3/2 minus 2 would be -1/2, that's not 3. So you know the t that makes that work will not make the others work. So you know this point is not on that line. That's a good thing to check first. You don't have to, but you did. Okay? Now, since they have it up here, I'm going to change this. Make this PQ cross U, isn't that what they use? Not a unit vector, by the way, and make this unit vector. Not a unit vector, U. Okay. What's that? Directional vector. That's what the U is. Okay. And we'll get to where we get that. So, what we need is some point on this line. Can anyone give me a point on that line? There is a very easy one. Okay? How you get a point on the line is pick a t, any t in the world. Right? -2, 0. 1. -2, 0, 1. Just take the constant here, right? T equals 0, that's what you get, right? It's the easiest one in the world. One of my favorite numbers in the world is 0. Well, that's why I like Ryan's. I mean, no, I didn't say that. Okay. All right. Now, so there is a point. We'll let this be our P, right? Now, let's do the vector PQ. what would that be? Pretty easy, isn't it? Please tell me yes. It's what? 5, -1, 3. Okay. And we're going to cross it with the u vector. Now, what is the vector that is the directional vector for the line that we had? Hint, to get the point on the line, we use the constants. To get the directional vector, we use the... Say again? Not the constants, the coefficients. 3, -2, 4. Okay. Now, to get that, well, if you look at your 3, -2, 4. If you look at the example on 793, you see that's what they use. But if you want where that originated, if you go back to Theorem 1111 on page 787, a line L parallel to the vector V ABC is then the line that has x1 plus at plus comma y1 plus bt comma z1 plus ct. Those are your direction numbers, a, b, and c, the coefficients of your parameter. Okay? So we're going to do this, take the magnitude of that, and then divide it by the magnitude of your direction vector, which was 3, -2, 4. Right? Yay or nay? Make sense?
That's the magnitude?
Yeah, that's the magnitude in numerator and denominator. Oh, okay, now this is no longer PQ. PQ was just the first part of it. Now this is D. Okay, I've just been building on myself. So first, how do we take the cross product of those two vectors? Please say you know. Okay, the I, J, if I could write, K, IJ. This is how I do cross products. And then 5, -1, 3, 5, -1, and 3, -2, 4, 3, -2. Okay? Now you're going to pretend to do a determinant of that, though you can't really do a determinant of a rectangular matrix. It has to be square, but this is just the easy way to do it. And then give me the first down diagonal. What you get? -4i. Next down diagonal, plus 9j. And the last diagonal, down diagonal, minus 10k. Okay. Then we'll do our up diagonals, which what's the difference here? You're subtracting those, so that will be a positive 3k. Is that what you said? Okay, I can't hear well. Okay. And the next one is going to be a positive 6i. And the last one is going to be minus 20j. Okay, add those together, and you get a you get a 2i minus 11j minus 7k. All right. Now we got to get the magnitude of that. A big boo hiss here, but doable. That would be the square root of, if my pen will ever write, 4 plus 121 plus 49. That would be 3 plus 121 plus 50. That would be 171 plus 3, 174. I did that fast in my head. I hope someone's doing it somehow. See if that's right. And then we got to do the magnitude of that directional vector, which would be 9 plus 4 plus 16. Well, 9 and 16 is 22, and 4 is 26. I think. Y'all do it and see if I got it right.
9, 4, 16 should be
29, okay. I wasn't doing very well, was I?
And on the top, you simply multiply the two.
Okay, hold on just a second. All right. What we did was take magnitude of this thing. That's the cross product of these two. That's what we just did. The cross product of these two gave us this. And that gave us a 121 and 49. That adds up to 170. Plus 4 is 174. Okay? And then the cross product of this one is 16 plus 4 is 20 plus 9 is 29. Okay. Now, right off the top, I don't see anything in common with either of those. 29 is a prime number, I believe, so it's not going to have any hidden squares in it. 174, unless this is a multiple of 29, which I don't think it is. Huh?
It is.
It is. Okay. 6?
Yep, 6.
Yeah, that would work. 6 times 9, 54. Yes, look at that. That would be 6. That's
Or square root of 6.
square root of 6. Okay, that's square root of 6. All right. Because 29 went, yeah, okay. Square root of 6, which is about 2.45. Okay. See how this works? Magic, isn't it? Okay.
Would you mind explaining how you find cross multiple numbers? So I, J, K, I, J.
Okay. How you do a cross product, is that what you're saying?
Yes.
Okay. Technically, you're just supposed to take that square matrix, which is IJK, 5, negative 1, 3, and 3, negative 2, 4. Okay? Then what you're supposed to do is I times the cross product here, minus J times the cross product there. And when I say cross product, it's the determinant. And the determinant, okay, let's start over. I times the determinant here. That would be a minus 4 minus a minus 6, that's a plus 2. That's how we got the I. The J, with determinants, you have a sign for every location. Plus, minus, plus, minus, plus, minus, plus, minus, plus, or plus, minus, plus, minus, plus, minus, plus, minus, plus. As long as you go left, right, or up or down, it always works out the same. So J is a minus one. So we're going to take the opposite of the cross product here. So that would be 20 minus 9 would be 11, but the opposite of that would be a minus 11J. And then the K, wipe out row and column there, and it's a minus, and that's a plus position, minus 10 plus 3 is minus 7. So actually that was about as easy as doing it this way, but so you don't forget that the J is negative, which is sometimes easy to forget. Doing it this way takes care of that. And besides, that's pretty easy to do too. But either way, this is how a lot of people like to do it. And what you do, you put down your original vector, which is IJK always on top, and then the two vectors you're multiplying down here corresponding to IJ and K, and then just repeat the first row and first column and second column, just exactly like they are. And then down diagonals are positive and up diagonals are negative. It just is another way of doing the same thing you did if you eliminate rows and columns.
It's easy.
Okay, I like it, but the other one isn't bad either. You just have to remember all your signs. This one takes a lot of the sign issue out of the way, okay? You just do it. And you get root 6, okay? And that, I believe, does finish 11.5. I'll leave this up. Homework exercises here would be number 5, which is found at calcchat.com. Any of the odds 7 through 11, they're found at CalcChat. 9's at CalcView. 13 or 15, they're both at CalcChat. 15's at CalcView. Any of the odds 17 to 23, all at CalcChat. 25 or 27, both at CalcChat. 29 or 31, both at CalcChat. 33 or 35, both at CalcChat. 37's at CalcChat. Any of the odds 39 to 43, all at CalcChat, with 39 being at CalcView. Any of the odds 45 to 55, they're all at CalcChat. 47's at CalcView. Either 57 or 59, both at CalcChat. 61 or 63, both at CalcChat. 65 or 67, both at CalcChat, with 65 being at CalcView. Any of the odds 69 to 73, all at CalcChat. 75 through 81, all at CalcChat, with 79 at CalcView. 83 or 85, both at CalcChat. 87 or 89, both at CalcChat, with 87 at CalcView. 91 or 93, with both at CalcChat. 91's at CalcView. 95 or 97, with 95 at both at CalcChat, 95 at CalcView. 99 should be at CalcChat. You can explore doing 101 or 103. Think about it anyway. It's up to you whether you do those. They should be at CalcChat. The modeling data in 105 should be at CalcChat. Distance problem 107 at CalcChat. 109, 111, either of those, they should be at CalcChat. There's some true false. 113 to 117, they should all be at CalcChat. And there's a little section project if you wanted to try that, distances in space. That's up to you. Now, the last section we're going to do in chapter 11, any questions on 11.5? Lots of practice problems there. Nay? Okay. The last section we're going to do in chapter 11 is 11.6. And this, believe it or not, is where Cal 3 normally begins, okay? But we hadn't covered all of in Cal 2, and that was a pretty important chapter, so we did. But always 11.6 is where you start Cal 3, or that's where it's supposed to be. So let's start it from the current slide. Chapter 11 is still vectors in the geometry of space, but 11.6 is surfaces in space. Not points or planes, but surfaces. They can take on lots of different shapes. Okay? We'll recognize and write equations for cylindrical surfaces, and we'll have to define what we mean by that. It's probably not what you're thinking. Okay? We'll recognize and write equations for quadric surfaces. Okay? You probably, unless you've had them before, don't even have a clue what they're talking about there. Has nothing to do with fours, by the way, even though it looks like it would. And we'll recognize and write equations of surfaces of revolution, okay, which is yet another issue, okay? So let's start with cylindrical surfaces. You've already studied two, okay, I'm going to back off of that a little bit. Surfaces of revolution were not in our course description. The only one that really was quadric surfaces, but most of the time they'll sort of include cylindrical surfaces with those. We're not going to do as much with cylindrical, it just introduce you to it. We may just do the same here, but we're not going to get too bogged down with that. The main thing here is quadric surfaces. So let's start with cylindrical surfaces. You've already studied two special types of surfaces, spheres. Okay? Now here is a definition of a sphere. What do these various things stand for? I'll give you one hint. The x, the y, and the z are your variables. So what in the world does the other things represent? X0, Y0, and Z0. Any ideas? that would be the center of the sphere. Okay? X0, Y0, Z0 is the center of the sphere. Well, this one's even easier. What's the R stand for? The radius of the sphere. So this is one definition or formula for a special type of surface, a sphere. Now, I like it written in a slightly different way. And what I'm going to do here is divide every term on both sides of the equation by r squared. Okay, so my new formula or equation for this would be, I'm going to rewrite it slightly different even from that, x minus x0 over r squared plus y minus y0 over r squared plus z minus z0 over r squared is equal to 1. It's no better, no worse than what the first one was. It's just another way of looking at it. Now, what gives it away that this is a sphere? Okay? One thing is the denominators are all the same. That happens to be the radius of the sphere. The second thing is that the coefficients of your variables are the same. 1, 1, and 1. Okay? If one of these coefficients was not 1, or one of these denominators was not r, that wouldn't be a sphere anymore. Okay? This makes it a sphere. The radii are all the same, and the coefficients of the variables in the numerator are all the same. Okay. Now, your planes, we just had that one just not long ago. ax plus by plus cz is equal, plus d is equal to 0, where a, b, and c would be the directional vector that this is parallel. I'm sorry. A, b, and c would be the normal vector for that plane. That was exactly our formula we used for that. So spheres and planes. And there's not much I want to do to change that. I kind of like putting the d on the other side, but that's just my preference. Yeah, that's beside the point. So a third type of surface in space is called a cylindrical surface, or simply a cylinder. Now, what do you think of when you think of a cylinder? Yeah, a Coke can, a tin can of any nature. Now, that is a cylinder, but it's a very special kind. It's a right circular cylinder, meaning the base is a circle and the base and the height is perpendicular to the base. Right circular cylinder. That's the one we usually think of. That's a very limited cylinder. Yes?
So if it's not a perfect cylinder, it would be like something that's not as wide as it is long, like maybe like a piston with those cylinders.
No, pistons would be right circular cylinders. Otherwise, they don't do too well in the cylinder. Okay, if they were anything other. Here, we'll get to it. To define a cylinder, consider the familiar right circular cylinder that we just talked about. The only difference is this doesn't have a top or a bottom. Okay, tin cans, Coke cans usually do, unless you have infinite Coke in there. Okay, the cylinder was generated by a vertical line moving around a circle. Okay, now a circle is x squared plus y squared equal a squared. That's a lot like that sphere, only it's only two-dimensional, where a is your radius. Okay, and again, you could have written this as x over a squared plus y over a squared is equal to 1. That's another way to write a circle. So a right circular cylinder has exactly the same formula as that circle that made the base of it, except you have three dimensions here, meaning the z does infinitely large, infinitely small, and doesn't change it. That is a right circular cylinder. A Coke can it's a finite. Okay, you chop off you put a bottom on it, put a top on it, and then you have a limited right circular cylinder. But all the rulings are parallel to the z-axis. Now the rulings are all those lines the vertical lines that you use to generate that right circular cylinder. So that is a right circular cylinder. Did you have to have a circle as the curve? No. Any curve will do. Okay? This circle is, the circle in this case is what we call the generating curve for the cylinder, as indicated by this following definition. Definition of a cylinder. Notice this is not a right circular cylinder anymore. Let C be a curve in a plane. Any curve in any plane. Let L be a line not in a parallel plane. So if this board is our plane, you can't use a plane that's parallel to it. But any line that's not parallel to this plane, a line not parallel to the plane, the set of all the lines parallel to L and intersecting C, that curve, is a cylinder. So if you did a sine curve here, okay, and I'm going to use it right, a line that does this. I've just made a sine cylinder, okay, a cylindrical sine. I mean, whatever you want to call that. It didn't have to be that. It could be a parabola. It didn't have to be a regular. Just take any line that, I'm using them perpendicular. They don't have to be. A line like this that follows that parabola. That has created a cylinder. Strange, but true. Any line not in a parallel plane, any curve that's in this plane, and let that line follow or generate, follow that generating curve. Another term for that is your directress, okay? That's where it has to follow. That defines the cylinder, whatever that generating curve of directress is. If it's a circle and your line is perpendicular, it's a right circular cylinder, okay? The parallel lines are called the rulings. They used the term on the previous slide before they defined them here. Okay, that's your definition of a circle. Of a cylinder. Here is, okay, without the loss of generality, you can assume that C lies in one of the three coordinate planes. It doesn't have to. It could be this plane right here. Yeah, you could, and then have a curve in that plane, and then have lines that are not in the parallel to the plane, and follow that curve. You know, that could work too. It's just easier to have it one of the three coordinate planes. Moreover, the text restricts the discussion to right cylinders. So we're not going to take those weird angles. We're always going to keep them right angle to the plane. Cylinders whose rulings are perpendicular to the coordinate plane, and then all you do is follow that curve, whatever that curve is. And that would be a cylinder. Okay. Note that the rulings intersect C and are parallel to the line L. Whatever your first one was, all of your rulings are going to follow that as you follow this curve with the rulings. Okay? This looks like, best I can figure, your curve is on the XZ plane here, and your lines are all parallel to the Y axis. Okay? Y axis doesn't happen to go through this curve, but they're all parallel to that. So you have a right cylinder here, but it follows this path here. Now, they just show a little bit of it. This is infinite. This way, into the board, away from the board, all infinite along Y, just like Y goes infinitely in this direction and that direction. Okay, that's the cylinder. Now, most of the cylinders we think of are closed cylinders. These are not. You don't have to be closed. Now, except for the handle here and the top and maybe a little bit of the bottom, this would be a cylinder, okay? It's not following a circle, it's following some other shape. So this would be the generating curve, and then the line that goes around here. Now, the handles don't fit in there, but everything else does. So it doesn't have to be...
It has to be a constant curve?
Okay, now that is a closed curve. A cylinder's right circle, a Coke can's a closed curve. These are open curves. They're all cylinders. And they're all right cylinders if the defining L, what do they call that? The goodness, the old gray cells, the rulings. The rulings are all cut through the curve on that plane and all perpendicular to the plane. Okay. Yeah, there it is right there, the rulings. Okay. So for the right circular cylinder that we were talking about before, Patrick's Coke can, the equation of the generating curve, that's what I was trying to think of, is x squared plus y squared equals a squared. Okay? That's also the equation of the right circular cylinder, because there is no z dependence on that. Now, if I was doing this one, I would do this like this. You know, of course, if that's the z-axis, you only see a quarter of that circle here. To find an equation of the cylinder, note that you can generate any one of the rulings by fixing the values of x and y and then allowing z to take on all real values. In this sense, the value of z is an arbitrary, therefore it does not show up in the equation. So the equation for your generating curve is also the equation, as long as it's right cylinder, that's it. In other words, the equation of the cylinder is simply the equation of the generating curve. I've just said that about 3 times. Okay. The equations of cylinders, the equation of a cylinder whose rulings are parallel to one of the coordinate axes contains only the variables corresponding to the other 2 axes. It could be that one they showed earlier was xz. It would be only the curve and whatever that one was. All right. So sketching a cylinder. Oh, I love this, don't you? Sketch the surface represented by each equation. Z is equal to y squared. What in the world is that going to look like? Okay. I hate trying to draw a 3-dimensional shape on a 2-dimensional surface, which is what I have to do here. Well, that be the z-axis, that's the y-axis, that's the x, y, and z. Okay? The number A there. What plane will your generating curve be on? Say again? Z and y, the zy plane. Okay? Now I see the zy plane, that basically is the plane of my screen here. Which way is this going, by the way? Up and to the right. I bet you're right there in some sense, but what do you mean by that?
Based upon the equation 1 is directly.
Is this what you meant?
Oh, yes.
A parabola like that. Okay. Where this is your negative y here. Here's your negative x somewhere back there. And your negative z is somewhere down here. And the negative z is not at all important. So why do I always go blank on that word? Rulings. The rulings are going to be parallel to which axis? Say again? No. The one not mentioned here. The x-axis. So these will be, so if these lines are parallel, these are this is the surface. You know, that's, they didn't come out close to parallel, but, you know, that would be the surface. All these should be parallel to the x-axis. Oh, none of them are they? Let's see if I can do that a little bit better. I hate doing this, okay? Okay. Actually, that part of it wasn't too bad. The rulings were terrible. Okay. I should be extending back this way and this way. These should all be parallel to the x-axis. Oh! That's not even on the curve. Okay. Oops, that one got off some. Okay. So basically, and that makes no sense at all, but basically you have a curve here, it just keeps going back. Everything, it's a trough with the bottom of the trough on the x-axis, okay? All back and forth for eternity, okay, in both directions, okay? It's pretty ugly. Okay. They were a lot gentler with theirs, okay? I think I'll erase it all. Is that okay?
Yeah.
Y'all aren't going to be heartbroken not to look at that anymore. Hey, that you answered too quickly. Okay. How about the B here? Again, I'll put my axes in here. X, Y, and Z. These aren't the best choice of axes, but they're the ones I draw best. Okay. Okay. Which plane are we in? XZ plane. So there's nothing along the Y plane. So I'm going to get this back here and this here.
The rulings are going to be parallel to Y.
That's exactly it. Okay. All right. Now, how does Z is equal to sine X look?
Isn't it a wave?
Yes, a wave. Okay. All right. I'm going to try to tick off my half pies here. 1/2 pi, 2/2 pi, 3/2 pi, 4/2 pi, 5/2 pi, -1/2 pi, -1/2 pi, 2/2 pi, 3, whatever. Okay. Going on back here. So those will start here, go up to plus. Whoops. Did that poorly right off the top. Okay. To the max, to 0, to min, to 0, to max, to 0. Okay. And then going this way, it's coming here, 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 here. That's supposed to be in the XZ plane back here, okay? And mine stinks, okay? Now, what the rulings are, they're parallel to the Y plane. So all these going here, every one of these parallel to the Y plane, and back here parallel to the Y plane. So what you have is picture. You have a blanket on the bed, and you do this to it, and that wave does like this, like this, like that. That's your sinusoidal curve, your sine curve in that direction. Okay? Oh! I should have started right here and ended right there, because it's 0 less than or equal to x less than or equal. So forget this part back here, which would be that, and anything past here. Ooh, took too much out, didn't it? That, okay. And then it says wave like that.
And the rulings are.
Oh, no. I got it upside down, didn't I? Sorry about that. You caught that, didn't you? Yeah, you were going to tell me that, didn't you? Okay. I was going positive in the negative direction. This starts and goes up and down and up. Yeah, and then the rulings are along the Y's. So that's what it looks like. Because your positive X is this way, and positive Z that way. So it starts out going to +1, 0, -1, and 0. Okay. All right. Those were fun, weren't they? Let's see how they draw them, as if they thought they could do better than me. Okay.
Bless you.
Y'all awake yet? Okay. The first on the graph is a cylinder whose generating curve is a parabola in the YZ plane. And see, they tilted the Y a little bit more than my head. Okay, thank you. Now, they show it only coming positive here. There's nothing that says it has to be. This would be going infinitely in both directions. There's the generating curve. Z is equal to Y squared, okay? And then it comes infinitely this way and infinitely that way. They only showed it coming a little ways this way along the x-axis. That's a trough. And again, the perspective really stinks here. This is coming out and up. This is going back that way. And that trough is coming out the x-axis and going back that way. Okay? That's it. Okay? The B one is the graph, is the sine curve in the xz plane. And it has to be going positive in this way. So here it's going up to +1, down to 0, down to -1, and then up to 0 here, stopping at 2 pi. So this is terminal. They did stop it correctly there. All your rulings are parallel to the y-axis. There it is.
Can it be parallel to the y-axis while moving positively along the z-axis?
Say that one more time.
Can it be parallel to the y-axis while moving positively up the z-axis?
Okay. All you're doing in Z is going back and forth between plus and minus 1. The Y is going infinitely in both directions. Your X is going from 0 to pi halves at the maximum Z, down to 0 at the intercept, down to -1 at the minimum Z, and then up here. But you're stopping right there. So your Y's are infinite. Your X's are only 0 to here, and your Z's are only -1 to 1. I don't know if that's what you're saying, but you're not going infinitely in Z because they stay between plus and -1. Just because sine does. Okay? These only go between plus and -1. This is going only from 0 to pi, 2 pi, but the Y's are going infinitely. So it's an infinite wave there. A really big blanket. Okay. Now let's do quadric surfaces. This is what we're supposed to be focusing on. The fourth basic type of surface in space is a quadric surface. Now, the only thing I can say is, just like a quadratic equation, the maximum exponent is 2. With a quadric surface, the maximum exponent is 2. Okay? So that's the only connection with quad that you have here. The quadric surfaces are three-dimensional analogs of the conic sections. So maybe we need to go back and review what in the world are your conic sections. Does anyone remember what that principle is? A cone is typically this kind of thing, right? Right. That's a cone. Okay? Not necessarily circular. It could be elliptical. It may even be irregular, but we're going to stick with regulars. Okay? In fact, we're going to stick with circulars. Okay? Circular cones like this. Okay? All these intersections here, if that is the, say, the XY plane cutting right through here, then these are all parallel to that, and they are circles. Okay? Now, to make it not a circle, do like this. Now you've made an ellipse. One axis is longer than the other axis. Okay? That would be an ellipse. Yay or nay? Okay? If you take a plane and cut a cone perpendicular to the axis of that cone, you're always going to get circles. Okay? Take a plane not parallel and cut this way, you always get ellipses. Okay. Now, take a plane and just cut through either the upper or the lower pieces down here, and what you get is a parabola. Okay? Take a plane parallel to the axis of that, and you cut here and here. Those are hyperbola. So those are your four conic surfaces: circles, ellipses, parabola, and hyperbola. Now, let's take the first one. Okay, here's how we usually write a circle. We've done it earlier. X squared plus y squared is equal to r squared. Okay? Or x over r squared plus y over r squared is equal to 1. Either one of those formulas is fine. Okay? Your ellipse would typically be this. X, I'll try to write it both ways. Ax squared plus by squared is equal to c squared. Now, I intentionally didn't use r because an ellipse doesn't have a radius. Okay? But what makes an ellipse, it looks a lot like a circular formula, except the coefficients here are not the same. Okay? Are not the same. Okay? Now, the other way to write this one would be divide everything by c squared, and that would give you, oh, and by the way, or you could just say c. You don't have to say c squared, but it usually is helpful. But anyway, your ellipse will be something like this. Now, I'm going to use the same letters, but for different reasons. If we had made this a squared, b squared, that would have been fine too. Okay. I'm going to skip some things here. X squared over a squared plus y squared over b squared is equal to 1. That's an ellipse. Now, what have I done there? I made the c squared over a this new a, and made the c squared over b the new b. Okay? So this is your sort of generic form for an ellipse. That works, but it's a little awkward. You can narrow it down to 2 parameters here. Just have this. The larger of these two, and by the way, to make it look like the other, this would be x over a squared plus y over b squared is equal to 1. The same thing, just square that whole thing. The larger of these two is called the major axis, and the shorter is called the minor axis. But you don't need to know that yet, but that's what it is. There's your ellipse. Right? Now, parabola we're pretty used to, right? Okay? The parabola is basically going to be something like this. We usually say it, y is equal to ax squared plus b, or something like that. I mean, you can put various letters in there, but in other words, one of the variables is to the first power, the other one to the second power. Okay? And the a determines how steep it is, how narrow it is, how wide it is, and which direction it's going. If A is negative, it's opening downward. The B is just a translation thing, which we're not going to worry about. But that's your general form of that. There may be a simpler way to do it, but I won't mess with it now. What your hyperbola is, okay, it looks a lot like an ellipse with one difference. There's your hyperbola. In generic form, you could write it like you did here. Ax squared plus by squared is equal to some c squared, or minus by squared is equal to some c squared. The key here is you have a minus sign over a plus. Okay? For circles and ellipses, both of the variables have the same sign for the coefficients. Always. For hyperbola, it's opposite sign. One's plus and one minus. And if you wrote that on the same side, your parabola would look like it would have opposite signs as well, except for the fact that's just opening up or down. Okay? In this one, this is the major, positive is the major axis, and the negative is the minor axis. Okay. Now here's another thing. If the A and B were the same, you still have a hyperbola, okay? Because of that minus sign in there. So generically we put them different, but they could be the same. These can't be the same, or they can, because a circle is a special form of ellipse. Is a special form. So now that you have what the conic sections are, let's see if we can figure out what the quadric surfaces are. The equation of a quadric surface, if you really want to know, in space is a second degree equation, just like in a plane, second degree equation is a quadratic equation. In space, a second degree equation is a quadric equation, a quadric surface. The most general form of this equation is ax squared plus by squared plus, and notice here we got three variables, not two. Conic sections are just two variables, okay? These are three variables. C, z cubed, that's z squared. And then they throw in a bunch of cross terms. dxy plus exz plus fyz plus, and then they put in the linear terms, gx plus hy plus iz, then a constant term, j. And that's equal to 0. That's your general form for any quadric surface. Okay? I'll just give you a hint. If the A, B, and C are all the same sign, you're going to have, and the same value, same sign and same value, you're going to have a sphere. If the A, B, and C are all the same sign, but at least one or all three are different values, you're going to have what they call an ellipsoid, okay? Kind of like a football, a little bit. If you're, at least one of these is negative, you're going to have hyperboloid. And you have two types of hyperboloids. We'll come back to that in a minute. What these three terms here and these three here do is get you off the, your axis is not a quadrantal axis, okay? So the cross terms here allows you to take this shape and twist it over like this or something like that. We're not going to do any of those, okay? And we're probably not going to have any there either of the linears, okay? If we did, all we could do is complete the square between these and those, and you come up with the offset. Your center will not be at the origin. It will be somewhere else. So the 6 basic types of quadric surfaces are ellipsoid, which is when the three signs of the A, B, and C are all the same. That makes an ellipsoid. Don't worry about the rest of it. Hyperboloid of one sheet, okay? That's where, we'll get to this later. Hold off on that one. Then hyperboloid of two sheets. So there's our two others. So you have two hyperboloids. Elliptic cone, which is going to be a cone like we started with the conic section, but now it can be elliptical, not circular. Okay, that's an elliptic cone. An elliptic paraboloid, and then a hyperbolic paraboloid. Okay, and we'll see what the differences are here. I don't want to go into the differences now until you actually get to see them. Because by waving my arms, I don't think it'll do a lot of good for you. All right, so those. So basically, there's ellipsoids, hyperboloids. Those are two types of hyperboloids. One elliptic cone, and then two types of paraboloids. One elliptic and one hyperbolic. So you're sort of crossing. Yes.
You said same sign and same value as a sphere, and then same sign with different values of ellipsoid.
Okay. Okay. Let's go back to this. For an ellipsoid, same signs for your quadratic terms. Okay. Either all three positive, all three negative. Okay. That's going to make an ellipsoid. Hyperboloid, at least one of the signs will be different from the other two. It will be plus, plus, minus, or plus, minus, minus. At least one sign is different with these three. Don't worry about the others. Okay. For a paraboloid, I didn't say that. I probably should have. Oh, elliptic cone. Let's just wait till we see that, because there's one little difference there, and we'll point that out when we get there. Let's go to the paraboloid. One of the square terms, at least one of the square terms is missing. You have either two squares and one linear, or you have two linears and one square, or something like that. But usually it's two squares and one linear. And that's what makes a paraboloid. Then one's elliptic and one's hyperbolic. Hold off and we'll get there. But that's why there's extra ones of these.
What if you should have a regular quadratic equation where it's a square, a linear, and a coefficient?
Okay. And all three, like you got here?
Square,
Or-
linear,
or-
coefficient.
Yeah, just missing those. Squares, linears, and constant. Is that what you were saying? This means it won't be tilted by one of the axes. It means if you just have this one and those without the cross terms here, your center may not be the origin. It may be displaced somewhere. But it'll still be a regular quadratic surface. Okay? Does that answer it?
No, that's exactly.
Okay. Now, the intersection of a surface with a plane is called the trace of the surface. The intersection of a surface with a plane, any plane, not necessarily a quadrantal plane, but just any plane, is called the trace of that surface. Okay? To visualize a surface in space is helpful to determine its traces with some well-chosen planes. Okay? So we're going to choose them well. The traces of quadratic surfaces are your conic sections. Okay? The traces of your quadratic surfaces will be these conic sections. Remember, circles, ellipses, hyperbolas, and parabolas. Okay? These traces, together with the standard form of the equation of each quadratic surface, we haven't gotten to yet, but we're getting close, are shown in the following table. So here they come. This is an ellipsoid. Okay? Now, like I said before, and this is why I gave you the alternate forms. Okay? The ellipsoid is going to be x squared over a squared plus y squared over b squared plus c squared over z squared over c squared is equal to 1. That would be an ellipse, right? That would be an ellipse. That would be an ellipse. So what I just did when I did that, I made z equals 0. With z equals 0, you're just in the xy plane, and that will be an ellipse in the xy plane. Here I did y is equal to 0. That would be an ellipse in the xz plane. And here I put x equals 0, and that would be an ellipse in the yz plane. Okay? So that's what it means to select a plane judiciously and do a trace in that plane. Okay? Now, remember, if that A, B, and C are all the same, you have a sphere. A is equal to B is equal to C, and they're not equal to 0. That would really mess everything up. That would be a sphere. But if any one of them is not the same as the other two, or all three of them are different, then you have an ellipsoid. But sphere is an ellipsoid. And then this is what I was saying here. Here is the xy trace. Just set z equals 0, and you got the trace, that ellipse in the xy plane. Set y is equal to 0, you get the trace, the ellipse in the yxz plane. And set x equal 0, and you have the trace of the ellipse in the yz plane. All right. Now, hyperboloid of one sheet. Okay? Now, what I want you to notice, at least so far, your standard form for your equations is what I was trying to suggest to you before. You put your terms with denominators and have it equal to 1. Now, we'll come up with one that's not equal to 1. That's coming later. Okay? This is hyperboloid of one sheet. Now, here's what makes that true. Let's say z is equal to 0. Actually, it will work also for z as any constant. Okay? Then, what you have is an ellipse. So, z is equal to 0, you form an ellipse right down here. Okay? Your xy trace will be an ellipse. However, if you do y is equal to 0, that gives you your hyperbola. So if y is equal to 0, you're in the xz plane here, and you see you have some on this side and some on that side. Those are hyperbola. And if you have x equals 0, that puts you in the yz plane, and again, they're hyperbola on either side. That's a hyperboloid of one sheet. Okay? It looks like that. Now, why do they say of one sheet? Because you can have a solid, not a solid, I guess you'd say, a single wrapping is all you use to go all the way around. There's no cuts in it, okay? One sheet. Now, how does that differ from a hyperboloid of two sheets? Well, here's that, okay? Here you have two minus signs and one plus, okay? Bless you. Okay? Oh, let me go back here. Notice, hyperboloid of one sheet, you have one minus sign. That's always your axis of that hyperboloid. Okay? Everything's revolved around that. Okay? Because this forms an ellipse around here. And in fact, for any z values, you always get an ellipse as your trace for any given z value. Okay? And that's what makes it one sheet, because it always works that way. Okay? Now, because you see, if you add this to the other side, that's a positive entity. So you always have a positive entity equaling a positive entity, so everything works. Now, when you go to two sheets, just think of this. Hyperboloid of one sheet has one minus sign. A hyperboloid of two sheets has two minus signs. Okay? Now, what makes this problematic? Okay? Now the one with the sign that's different from the others. This time it happens to be positive. This then makes this your axis here. The other was when it was only one minus, that made the z your axis. This makes the z your axis here. Okay? Now, think of this. If you had added this to that side and that to that side, everything over here is positive. This certainly is positive, right? Agreed? Okay. Now, no, I'm sorry. Yeah, no, that's right. Okay. But there is no value in the world which can make z equal 0. Because if you added this to this side and that to this side, then even if x and y were both zeros, you still have a 1 there. Okay? So z can never be 0. So in other words, it doesn't it doesn't intersect the origin. Now notice they've left off all the terms that would move the origin or the center of your figure around. We're just dealing with the quadratic terms, and later we'll introduce the others. So this is a hyperboloid of 2 sheets. Okay? 2 minus signs. Okay? Your trace are ellipses. When they're parallel to the xy plane, they can't be on the xy plane, because on the xy plane, z is equal to 0. Here's the other way of looking at that. Z is equal to 0, right, on the xy plane? This is a negative number, that's a positive number. Not going to happen. Can't possibly happen. So therefore, this makes it a 2-sheet. Are we out of time?
Yes.
I gather we must be, by the way people are moving. All right. How far did we get? We got on the table through 2 sheets. So we'll be beginning next time on elliptic cones. Okay? Let's see if there's any homework exercises you can do. Okay. Now here's a question for you.
What's the question?
Before you go, homework exercises I would say, do number 5, 6, no, you can't do 6, odds. 5, 7, 9, 5, 7, or 9. Any one of those. They're all at Calc Chat. I think you can do 11 or 13. They're both at Calc Chat. 11 at Calc View. And stop there. But before you go, here's a question for you. Do you want to start your test? Even though we haven't finished 11-6, you can just forget about 7 through 10. Now what I did, since I already had one made up, this isn't going to cover everything we covered in 11 as a separate question, but everything we did is somewhere in these questions. Okay? It really looks like it's just 11, 4, 5, and 6 or something like that. Don't worry about 7 through 10 yet, but you should be able to do 1 through 6 if you want to. Okay? If you don't want to jump on it, you don't have to. Are you likely to see Josh?
I mean, he might be here tomorrow, so.
I'll see him. Well, if he is, I'll give it to him. Okay. But you don't normally see him otherwise. Okay. All right. We'll pick up and go from there. All right. No extra charge for the extra time today. Okay.
See you Monday.